Yeah, I think it's coming back on. Final live. No, it's live. I just need to mute it on the YouTube side, otherwise you feel yourself like 30 seconds later, which is not optimal. That would test your focus. Oh, wait, Karen. No, so you know, okay, yeah, I can actually do it.
What?
Good. Okay, hang on. Let me go back to the. Yeah. Okay. Do we have? I just want to make sure the participants is. No, yes, it wasn't here. Martin, maybe. So good. In a minute. Did you see the? You don't follow tennis, do you?
Pardon?
No, none of you follow tennis.
But there's the gymnastics one soon.
The gymnastics,
Yesterday
no.
was the
Tennis.
first.
Yesterday there was a gigantic match between Murray, who has the same artificial hip that I have, and another guy from the US. 3.5 hours. The poor guy.
Did you watch it?
We part of it. I know 3.5 hours. I taped it. Oh, there's Burkhard. Good to see you.
Good to see you.
Yeah. No. It's trickling in there slowly.
Where is our speaker?
It's true, yeah. We got double the, double the whammy. It's gonna give you a talk in stereo.
Good.
You know if Martin is available today, or?
I have no idea. I was in a meeting all day.
Oh, yeah, I had a lot of. Now it's busy nowadays, yeah. So, okay. So let me start now, since it's officially 3 o'clock. So thank you, everybody. I come once again to the online SPICE-SPIN+X seminars organized by the Spin Phenomenon Interdisciplinary Center that I lead together with Karen Everson City, who is now a professor in Duisburg, and the Collaborative Research Center SPIN+X, that is led by Martina Schliemann and Burkhard Hillebrands in Kaiserslautern, together with Matthias Chloe in Mainz. As you all know, this is a Zoom webinar format, so please, you will see, of course, the speaker and whoever is speaking, and ask your questions afterwards. I will give you the floor to, I will promote you to panelists, and you can ask the speaker directly your questions. As usually, we have a 3 p.m. slot. And next week, just for announcements, Christian von Verma will be giving the talk. Today's speaker needs very little introduction in our field, actually. Achim Rosch is professor at the University of Cologne, and he has received many prizes. Highlights maybe here is the Leibniz Prize in 2013 and the European Physics Prize in 2016 for the work particularly on Hermian physics. But he's actually very well known for astronomy related behavior studies, as well as being very broad physicist in his approach to the science. And in that sense, it's always a delight to hear from him. So with that, we'll stop sharing. And Achim, when you would like, share your screen.
I do like, because it's a special pleasure to be here and giving this seminar. Good. So welcome, everybody. And what I want to do today is to present actually a work which has been done mainly by Nina Delcer. Here's her picture during her PhD thesis with some support from Lucas Heinen, who was mainly doing the numerics of what we're talking about. And I want to tell you a story of driven magnetic systems, and you'll see that the Archimedean screw will be the hero of our story. And but let me mention for the friends of skyrmions, there will be kind of some added material with dancing skyrmions at the end if we come to that. Good, but let me start, and let me start with some general questions you can ask, namely, well, what type of simple machines can we actually use to and build using driven quantum matter? Yeah, and we don't want to do something fancy, but something very basic to start with. And one of the things which naturally, and the first question is, why should we do that? And I guess there are two main reasons. Namely, we can use these small machines to explore physical mechanisms and fundamental concepts to describe, for example, non-equilibrium states of matter. And finally, we may also hope to create something useful. So my own heart is more with the first part, but maybe you also find something in my talk concerning the second point. Good. So what type of picture do we have in mind? And we want to look at one of the oldest machines invented by mankind. And it's a machine invented by Archimedes. And he used that and he invented that actually to train ships. So ships filling with water, and you want to get the water out of the ship. And I think Archimedes is one of our heroes in the sense that he was a very early physicist. So he really combined mathematics, engineering. He was an inspiring inventor and was able to combine these concepts and create something new and also some useful stuff. So that's, we want to follow his step. And the first thing we should do is we should think is what is really at the heart of an Archimedean screw. So the job of the screw is transport some things using a rotation. And and we want to do, and the same principle is not only part of the Archimedean screw, but actually any screw has this property. So what we want to do is we want to rotate something and get now our screw in the wall in this example. We want to have a translation associated with this rotation. So that's what a screw is about. And now, so we are now here in this magnetic context. So it's pretty obvious what type of screw we want to take. Namely, we want to take a helical magnet. So just a magnet whose magnetization smoothly rotates in space. And we look at a system actually with a spin-orbit interaction. And that makes sure that this rotation of the spin is actually locked to the translation mode. So when we rotate this spin structure or translate the spin structure, it has this net same effect. And the interaction locking the two is given by the spin-orbit interaction. Good. And now, as most of you will know, nature provides us with hundreds of different materials of such helical structures, and some helices have just a pitch of a nanometers, some micrometers. We have them in metals, insulators, semiconductors. We can have them at room temperature, at low temperature. And I'm coming a little bit to this part of the field from the skyrmionic side. So essentially all these skyrmion materials are good candidates. And indeed, the simplest and cleanest case, and that's the one which I will base numbers and quantitative aspects of, are these cubic magnets without inversion symmetries. So materials like manganese silicide, copper selene oxide. So these are the prime materials which we have in mind in this context. And they form all nice, perfect helices with pitches ranging 50 nanometers, 100 nanometers, something like that. Good. So I'm a theorist, so there will be a few formulas in this talk. And here is what we want to do. So we take our theory, which we know describes very precisely one of these helical magnets. So most importantly, we have here the Choleshinski-Moria interaction, which says the system gains energy when it forms these helical states of matter. And we put, what we simply do is we put the whole thing in an external magnetic field. There's a uniform magnetization which fixes the orientation of this helix. So this would be oriented parallel to the external magnetic field. And then we add to that a small oscillating magnetic field, just a few millitesla if you want to think about an actual experiment. And then our job obviously is to look for the dynamics of the full system in the presence of a little bit of damping, which could be come because this is a metallic system, for example. So let's try to describe this theoretically. And first thing, and we do this now in good old perturbation theory. And we start by ignoring the perturbation. And then we said we have this simple conical state. So it's this helical state of matter where the magnetization forms this helix oriented in z direction. Now we look what happens in linear order in this perturbing term here, and it oscillates to the frequency omega. So it's clear that we get the magnetic state will also do some oscillations, and that has been well extensively measured by various groups. There has been some here for these Kerman materials. There has been some early work, and what you see in this in the conical phase, you typically see two resonances, which are actually the splitting comes from the dipolar interaction in these systems. And we know exactly how to describe this theoretically. We get a very perfect agreement between theory and experiment for such systems. Good, so that's standard linear response theory, but now we want to go one step further. And for this, we actually have to go to second order in the oscillating magnetic field. And then it's clear we are now to second order, we get a response at frequency 2 omega and also at frequency 0. And so the 2 omega is boring for our purposes, so we're not interested in this higher harmonic generation, but we know that something interesting could happen at frequency 0. Namely, at frequency 0, our system has a Goldstar mode, and the Goldstar mode is actually nothing but the translation of the helix, or the rotation of the helix, if you like. That's actually the same Goldstar mode. So that's where our screwing action is setting. So let's look a little bit how that goes. Yeah? So I'll want to guide you a little bit through the analytical calculation, but don't worry, you don't have the precise formulas don't matter, but I want to show you a little bit how that goes. So what we do is we just solve the dynamics order by order in perturbation theory, and to linear order, let me just mention that this helix is such a simple magnetic structure that you can get everything fully analytically, and this here's the frequency, for example, for the resonance frequencies, and I'm just showing you to show off that one can really do this type of calculation without any problem. But now, so linear order is boring. We want to go to quadratic order, and there you get some lengthy formulas. Here's a super simplified version, which is when you forget about dipolar interactions, but we actually have done this with full dipolar interactions. And now, how do you solve such an equation? Well, you just do a Fourier transform and then find a solution. That's the game you usually do. But when you do that, then you find out actually these equations just don't have a solution. So that's kind of unexpected until you realize that you should search for something where this angle, which describes the translation or rotation of the helix, increases linearly in time. Yeah? And when you allow for this term linear in time, then you can easily solve these equations. So messages, we do linear response theory, and then we get a diverging response at 0 frequency. So that something is linear growing in time means you have a diverging response, and that has a very simple interpretation. Namely, our screw is doing what it should do. It's namely doing this screw-like motion. So let's look how that goes. So on the right side, you see a small simulation. Well, it's kind of moderately well transmitted here via Zoom, but I think you get it. So what we have is we have some rapid oscillation on the frequency of the applied magnetic field. And then we have a slow screw-like motion going on a much different time scale. And actually, when you put in numbers, then in these B20 magnets like copper selene oxide, the resonance frequency would be in the gigahertz. So we drive this resonantly at the resonant modes of the system, and we get out a screw-like motion in the megahertz regime. And later I will argue that this is actually still a pretty efficient screw, but let's postpone this discussion for a second. And what you should see is that this direction in which the screw is moving, whether it moves up or down, can be, for example, in this case, controlled by the frequency which you apply. So when you go to one resonance frequencies, you have screwing motion to the left, and if you go to another frequency, you have screwing motion to the right. And what you should also see here is that we can really understand this fully analytically. Namely, the solid line is the analytical calculation, and the blue points are actual simulations. So obviously, one can we have good control about this physics. Good. So good news. We have found a solution for this Archimedean screw, but that's only the beginning. So now we want to see well, how stable that is. That will be the first part of the story, and then what can we do with these types of screws? That's the second part of the story. But let's first look for the stability of the solution. And maybe we first start just at steroid numerics. And what I'm plotting for you is just the angle of a single spin. So how a single spin is rotating. And now we first apply a very weak field here, a fraction of a millitesla in this equation. And what you see is that via oscillations, this angle is slowly growing. And this is just our Archimedean screw at action. So we have the helix moving or rotating, just driven by this magnetic field. Good. But now, when we increase the amplitude, then you see something else is happening. Namely, on top of the frequency imprinted by the external magnetic field and this linear slope, there's suddenly a second frequency showing up here. So the system builds up a second frequency. So if you want, you could formulate it like that. We spontaneously break time translation invariance. So what we do here is we form a time crystal, or more precise term would be a time quasi-crystal. Quasi-crystal because it turns out that this frequency which we have here, and it's actually periodic structure in space and time, which I'll show you in a second, is incommensurate with the driving frequency. So the frequency in which the magnetization is oscillating is now a new frequency, and it has nothing to do with the underlying driving frequency. And finally, we get some chaotic solution. So, and the physics, what we see here, I think, is a very generic behavior of such a driven non-collinear magnet. And as it's so generic, I want to discuss that behavior here also from the analytical point of view and explain to you where this is coming from. So, and another reason why we look for this from the numerical side is also, it turns out that especially in this strongly driven regime, the numerics alone turns out to be rather unreliable in the sense that it's very strongly affected by the size of the simulated region. So it was only after we got a full analytical understanding of what's going on that we really trusted also the numerical results. Good. So what we should do now is we should look at the stability of this Archimedean screw solutions. And for this, we have to look at the magnons. And what I'm plotting here on the right side is nothing but the Magnum spectrum of the system. And more precisely, this is the Magnum system of the unperturbed system. So we have not yet switched on our gigahertz oscillating field. And we just look at the excitation spectrum, but we do it in a special way. Namely, we plot the energy modulo the frequency omega. And the reason is later in the driven system, energy is only conserved up to multiples of the driving frequency, and therefore we look at the energies modulo omega. So on the top we have the energies, on the bottom we have the decay rate, and there's the Goldstar mode in the middle, describes that has zero energy and zero damping. Good. Now we proceed. Now we look at this spectrum, and what we see is that this unperturbed system naturally has crossings of these excitations, and these excitations have and these crossings, the ones which are important for our purpose, have a very simple interpretation. Namely, these are points of resonance where the magnon of some magnon band I plus the energy of some magnon band J at momentum minus K precisely fulfills the resonant condition. And in a sufficiently complex spectrum of a non-collinear magnet, we will always have such points where we can now resonantly emit magnon pairs. So if this condition is met, then I can use the energy to create correlated pairs of magnons. And now we have to ask what happens to these points when we now increase the driving energy. And what you see is now when you increase the amplitude and you do the calculation, then first the spectrum here is changing slightly, but more important is what happens to the decay rate, namely, or minus the decay rate. Namely, what you find out is that the imaginary part here of the spectrum shrinks, namely approaches zero, so the decay rate shrinks, and then it changes sign and you get anti-damping. So you drive the system, and then, not surprisingly, maybe you find out if you drive it sufficiently strong, then you suddenly get essentially a laser out. Yeah? So a laser which emits these pairs of magnons. And that will happen, as I said, in any of these driven systems because of this pair creation stability. Now in this system, you can look up where in momentum space this is happening. And the leading instability turns out to be here for momentum in the parallel direction, perpendicular momentum being zero. And precisely at these momenta and precisely at the frequency set by the condition, we do get our instability. Now my screen is not moving to the next slide. It's interesting. So let me, maybe I quickly stop screen sharing and share again.
Yeah, I think that should be.
That's
typically fixes it. If not, we have the backup. So
okay. Okay, this one I didn't have up to now, this effect. Okay, so
still
I stop again and good. I actually have a backup computer here.
Yeah.
Well, I didn't expect that I can use that I need to use that one, but I'll now switch to the backup. So it was good to have this
okay
backup, and now you should
need to move to the correct slide.
Okay. So
Okay. Understand.
So my apologies. I have to now to handle the second computer.
I'm seeing, can we build small machines using driven quantum matter? Yeah.
Okay, so I need one more second. Now, come on. Good. So now I'm hopefully operating back. Can you hear me?
Yeah, we can hear you.
Very good. Okay, my apologies for that. Good. So what I was going to tell you, that when we increase the driving amplitude, what we hit is naturally instability. And this instability means that we get this coherent emission of Magnum pairs. And in practice, this means that time translation invariance is broken, and I get a time quasi-crystal. And this is what you see here. So we increase the driving amplitude, and then precisely the point suggested by the analytical treatment, the system gets unstable and the time quasi-crystal forms until at some even higher amplitude chaos sets in. So let's take again a look what we are doing here in a slightly different version. So we start with small amplitudes. We have our Archimedean screw, and you can view this, and this screw-like motion really shows up when we now plot the angle of one of these spins as such a traveling wave along the screw. But it's really the full helix is now rotating. Now, when we increase the amplitude, then you see that a second frequency shows up, and also a second momentum shows up in the system. So we get this time quasi-crystal. And finally, when we increase the amplitude even more, then we enter a chaotic regime. And that's the same physics you also see when you do a kind of corpuscopic image of the time evolution of a spin. Then you get a similar behavior here. Good. Now, let me emphasize what we discussed here is a very generic properties of Magnum systems, which are driven by some oscillating magnetic fields. So I give you just one example, but what we are seeing here is not specific to this one case, but it's really something very generic. So let's recall what the main results are. So let's assume that we have a system with some Goldstar mode, yeah? And for example, when we have an incommensurate magnetic order, then there's always a Goldstar mode related to translations. Yeah? So I have some incommensurate magnetic state, and it costs no energy to move that, so that one has always a translational Goldstar mode. And now, at least if we ignore pinning, we'll discuss that later, then when we drive the system somehow by an oscillating field, then we can expect that some motion sets in. Now in our case, we describe it by frequency, but you could also say this is described by a velocity, v. And this velocity will be proportional to the amplitude of the driving field squared. Y square. So to linear order perturbation theory, we get a response at omega. To second order perturbation theory, we get a response at 2 omega at frequency 0. And this response at frequency 0 is that one which drives our Goldstar mode. So this is message 1. If symmetry allows, so if there's not some specific symmetry prohibiting that, then we are guaranteed that when we drive a system and look at second order response, we can activate some translational motion. Message 1. Then second message now is that when we have such a driven system, it naturally also has instabilities, because it may happen that if you look at the Magnum bands of the system, that you can find two bands with momentum k and minus k. So k is just arbitrary. where you can have resonant generation of Magnum pairs, and then you develop an instability with this momentum and this frequency. So this is also very generic and not specific to the system. And now the question is, when does this instability happen, or why does it not always happen? And it does not always happen because there's always Magnum damping. So this damping can be extrinsic or intrinsic. So extrinsic means there's a metal underlying, and the metal or the phonons are doing the damping. Or you can have an intrinsic damping, namely that the Magnum with a high frequency can decay in many other Magnums of lower frequencies. In both cases, certainly favor stabilize stabilize the original solution, so the original moving solutions, or our screwing, so our Archimedean screw. While when now this resonant equation of Magnons becomes too large, then the most natural consequence is that indeed you get a kind of Magnum laser, or in other words, you have now this oscillating texture with the is established with this frequency and this momentum, and that's the time quasi-crystal I was talking about. Now, what is and I should add what I should add here and have not written here is then if you increase the intensity even further, then something complicated sets in. Now, I argued that so in our numerics we get a chaotic solution, but the more precise statement is that that this happens in a regime where we can't really trust our numerics. So there, the onset of chaos will be is very strongly system size dependent, and to what extent the system will essentially heat up and magnetic order gets lost, or whether there's a chaotic magnetic motion of the magnetization is happening that we are not so sure about. Good, so let's come back to Archimedes. And as you know, it was the job of Archimedes to transport something. So we want to transport some water out of the ship, and now the question is, can we pump something with our Archimedean screw? And there are three obvious candidates for that. Then we can pump charge, we can pump heat, and we can pump a spin. And we were actually focusing on the simplest case, which is a charge pump. So here's our setting. So now we have to add some electrons. We want to pump charge, and we couple the electrons via exchange coupling to our Archimedean screw. And now I want to emphasize two elements which are really super important for the following story. First, we have to take into account some spin orbit interaction in the in our metal, otherwise nothing will happen. And second, we should take seriously that there's disorder in the system. So let's go along these lines. So first, let's do something very simple. Namely, let's pretend that we have no disorder, no umklapp scattering, nothing, and ask ourselves what will happen then. Then it's actually a pretty simple or trivial situation in the sense that we now have that we have our screw which is moving, and it will happen actually what you naively expect, namely just the electrons are flowing with the screw. So if our screw is moving with a certain velocity, the electrons are moving with a certain velocity, and then we can easily just calculate the current density by multiplying current, by multiplying velocity and electron density. It's as simple as that. So this is the clean limit. But now we have to take disorder seriously. And then it's a very bad idea to go to a co-moving coordinate system, because you don't want to have all these impurities flying towards you. But impurities are located in space. So what we technically do is now we go to a frame which is now not moving in time, so it's stationary in space, but we are still orienting the spin quantization axis parallel to the direction of my local magnetization. And if you do that, then the only term which continues to be time dependent arises from the spin-orbit interactions in the metallic system. So we go to this coordinate frame where the spin quantization axis is always parallel to the local magnetization, and the price we have to pay, or the only interesting term which is surviving, is now a term arising from the spin-orbit interaction, which is now oscillating in frequency, with this frequency describing this screw-like motion of the helix. Good, and now the job is to see whether such a term creates a current. And you will not be surprised to hear that this is indeed the case. If I have now this oscillating term, then it naturally creates a current. And at least if you're willing to ignore vertex corrections, then you can just straightforwardly calculate this in second-order perturbation theory. And what you'll find is that, yeah, so let's look what you find. So what I'm showing here is the electronic current as a function of the electronic lifetime zero, so a tau, sorry. And on the right side, we are in the clean limit. So there the electrons are just flowing with our Archimedean screw, and we get the maximum possible current, which is velocity times charge density. Now, in the super dirty limit, on the other hand, so when the lifetime goes to zero, obviously, you will not be surprised to hear that there's no electronic current happening, but there's an interesting intermediate regime where the current is actually proportional to tau, so the scattering time tau, and it's proportional to the strength of spin-orbit coupling squared. And this is actually the regime which we are interested in, and we can have systems with very large electronic lifetimes. So, for example, when you take a material like manganese silicide, which forms these beautiful helical phases and skirmion phases also, then you can get easily a mean-free path of, let's say, 1,000 angstrom, and then you are deeply in this regime where we get this linear dependence on the current on the scattering time. Good, so let's actually try to play a little bit with numbers and look how large the effect is which are predicted here. So we said we drive the system with gigahertz frequencies, which are these natural resonance frequencies of our conical phases in these cubic chiral magnets. And typical wavelength is, let's say, 20 nanometer, 200 angstrom. And when you translate this to a velocity, what you find out is that these screws move with a speed of let's say 20 millimeters per second. So that's a typical speed. Now you could ask, when I make the theoretical prediction, I was ignoring something which is absolutely essential here. Namely, I didn't tell you about the role of disorder, namely the pinning of the helix by disorder. So the question is, could be that the pinning of the magnetic structure to the disorder in the system, could this stop the physics from happening? But there we can think what we learned on pinning when we looked at the physics of skirmions in a material like manganese silicide. There we found out that we can get skirmions moving by very small forces in manganese silicide. So the typical velocity of these fermions at the depleting transition were of the order of 0.2 millimeter per second. And now we know that the forces for pinning of fermions and these helices are very similar, and therefore we can expect that the scales for the scales of the velocity will be similar. And you see that we are here safely 2 orders of magnitude away from pinning physics. So we definitely expect that at least in this material manganese silicide, which is very clean and very well behaved, we should have no problems whatsoever with pinning. So the second question is now, here stated again, pinning is not a problem, at least in these super clean systems. It may be different when you grow some layered materials by pulsed laser depositions. They are much, much dirtier, and then this pinning may be a serious issue. Now, the question is how big, actually, when we talk about 20 millimeters per second, what type, so how efficient that is that when you want to pump charge? So we can use our theory and now make some rough estimates in what order of magnitude of currents we expect for this type of velocities, take into account what is the amount of disorder in the system, take into account what is the strength of spin-orbit coupling in the system. And if we plug in all numbers, then we get current densities. So rough estimate is between 10 to the 3 and 10 to the 5 amps per meter squared. And I would say that's remarkably big. Obviously, when you now attach a voltage probe to a system, so if you have a finite system, then instead of the current, you will get a voltage. That's definitely something you can't miss. Yeah? So these are really giant effects. We're not talking about something small, but you really are able to transport a lot of charge through the system, and one should be very easy. It should be very easily to measure this effect. Good. Obviously, when you want to really build this experimental setup, you have to think a little bit how you shape your sample. For example, if it's a metal and if you want to transport charge, you better take a metal. You obviously should make the sample thinner than the penetration depth of this gigahertz radiation, which we need to drive the system. And we should think about surface quality and things like that. But the numbers look very good in this respect. Good. So I'm coming slowly to the end of my talk, and I want to switch gears. And I also argued that the principle we are discussing are very general, and so the natural question is, can we move also other stuff? No? So other stuff than just these helices. And the answer is obviously yes. And I gave you the argument that we can play this game with almost anything. And and one thing which comes to one's mind immediately is thinking about a magnetic fermion, because we were all the time discussing materials like manganese silicide, which hosts these fermion phases. Yeah? And for the moment, let's think about a magnetic fermion, so magnetic whirl, a single magnetic whirl embedded into a ferromagnet. And actually, we were by far not the first looking at this problem. There's a beautiful paper, and very insightful paper here by the Fangor group, which looked at this many years ago. But I thought it's still amusing now in this context of this talk to remind you about what can be done with just a fermion. And the movies I'm showing you in a second are from the master thesis of Bernd Krause-Juttermann, who looked at this also some time ago. So let's start straight ahead. And now we want to drive a magnetic fermion. And the way we want to do that is first realizing that moving a single fermion doesn't cost any energy, because so just translate it in space. So here also the translations are a Goldstar Mode of our system. So that's clear. And now we want to excite it efficiently. And a natural way to excite that is to look at the breathing mode of the skyrmion, which means you apply a perpendicular oscillating field, and that changes the size of the skyrmion. So the size of the skyrmion will oscillate back and forth. Now to make this a translation motion, we have to break this rotation symmetry somehow. And there are plenty of ways to break the rotation symmetry. And one is, and the simplest one, and that I will use next, is just to tilt the magnetic field a little bit. So we take a planar system and put the magnetic field not in perpendicular direction, but tilt it a little bit. But instead, we can also encode the symmetry breaking by the oscillating field. We can use the edge of the sample and use other skyrmions. All that is working very well. Good. So here is a movie. So what you see on the right side is a caterpillar, and the caterpillar has a special mode of motion. Namely, it comes closer and stretches again. That's actually pretty similar what our skyrmion is doing when we excite this breathing mode. Namely, it changes size. And now, if symmetry is sufficiently low and we have a little bit of friction, then this periodic size change is also associated with a translational motion. That's precisely what's happening here. Good. And so now you can, for example, study how does that depend on the exciting frequency. And as expected, the signal is largest when you tune your frequency to the breathing mode, to the eigen mode, which makes this oscillation of the skyrmion size. But actually, it turns out you can also do something else, namely you can just excite the chiral mode of the background magnet. So just the oscillation of the background, that works as well, and that also helps you to get this motion. And if you plug in numbers, then you can get here velocities for the skyrmion similar to the velocities we just discussed for our Archimedean screw. So a few millimeters per second are possible. Good. So now I want to go for a slightly different setting. Namely, what we used here is we used the tilted magnetic field to break the symmetry. But instead of using a tilted magnetic field, I can also use a field just in perpendicular direction. So all magnetic fields in perpendicular direction. And we use a second skyrmion to break the symmetry. Now we have two skyrmions, and we apply an oscillating magnetic field in z directions. And now in the following, I will not use a sinusoidal motion of this external magnetic field, but do something else. So let me show it to you. I'm not sure how much you are hearing me, so let me switch that off. So we have been modulating now for the simulation. We have modulating the external magnetic field by the sound amplitude of this waltz by Strauss, so An der schönen Donau. And we obviously were rescaling now the frequencies of our system so that the resonance frequency of our sound of our skyrmions are in the resonance spectrum. And now what happens is that the one skyrmion deforms the other skyrmion, and now we have the symmetry broken, and this broken symmetry allows now for a net motion. Actually, what happens is there's one force pushing these two guys together, and simultaneously we get this net rotation. When you want to improve that further, then you should change this type, your type of music. Namely, even better than using a waltz by Strauss is to do something else. Namely, if you want to do that, then so bagpipes are much more efficient, and the reason for that is that in a bagpipe there's always one pipe playing a sound with the same frequency. And now, if you want to have this Skyrmon dance in a very efficient way, so what you should do is you should tune one of your pipes to the Skyrmon breathing mode. So to this mode, changing the size of the Skyrmon. And then you get this very efficient motion of Skyrmons around each other. So obviously that was kind of a fun part, but it has a seriously underlying message, namely that it's very easy to move things around by oscillating magnetic fields. We typically have a Goldstar mode. Whenever it's allowed by symmetry, we pump in this Goldstar mode, and we can use that to realize novel charge spin and heat pumps, but also play some other games. So let me close here. Oops. So the main message of my talk was that we can use this activation of Goldstar modes as a very general principle applied to all types of Skyrmon helices. But especially interesting system are indeed these conical systems which realize an Archimedean screw. And the idea is the old idea of Archimedes to translate a rotation into a translation and then really pump charge, spin, and heat in these systems. And I think I would really love also to see some experimental realizations on that. I know that some groups are working on it, but I have not yet seen a nice experiment on that. But maybe there's somebody in the audience interested in this. And then I was also talking about a second story, which is also something very generic for different systems, that it's very natural to create some sort of Magnum lasers in these systems, and which define some type of time quasi-crystals. Yeah, and with that, I would like to stop and thank you for your attention.
Yeah, thank you very much, Achim. That was fabulous. So, of course, we'll take questions now from the audience. Please raise your hands to ask questions first. The first one is from Mikhail Moskalets. Can you unmute yourself and ask your question? And Achim, if you want to maybe turn on your camera. I don't know if you have a camera on your second laptop there.
Oh yeah, sorry.
Okay.
Sorry.
Good. Achim, thank you very much for your nice talk. I have a very simple question. Can you arrange setup when your pump can pump heat without pumping charge?
Mm-hmm. Yeah, so obviously, obvious thing is let's go to an insulator first. So we just don't take a metal, but we take an insulator, and then we'll have naturally no charge flowing. But heat is flowing, but maybe more interesting, spin is flowing. Because so heat pumps, so then maybe, so the system, I put energy in the system and maybe everything gets a little bit warmer. And then I'm not sure whether you see the cooling on one side. So the heat pump would mean I get cooling on one side, and I'm honestly not sure whether this will really win if everything is said and done. But I think more fun actually is to think about spin pumping. So that you get really an accumulation of net magnetization on the top, and we know very well how to measure this with inverse Hall effect and stuff like that. So I think heat pumps is nice, but maybe not so nice. But spin pumps would be the thing I would go for in insulators. And in metals, obviously, the charge transport, if you just take a final sample, then then obviously a voltage will build up, which will stop charge transport. Yeah. So if I just take my finite sample and have no, I don't attach some light bulb to it, then obviously the charge will stop flowing at some point, and then only spin and heat will flow.
Yeah, basically, I mean that in metal, when you don't apply voltage, when you don't apply bias, but just drive your system from inside, you excite electrons and holes. And if you pump them in parallel, then you will not pump charge, but both of them will carry energy, carry heat, so you will pump heat.
Yeah,
this is basically what I mean.
Yeah, so it's true that—
Is it possible or not in your system?
Yeah, I think obviously we designed it just the opposite way. So we want to have the
okay, I see.
But,
okay,
but it's
good.
very net, so we have this screw moving in one direction, and so you need a lot of fine tuning to avoid
Thank you very much.
Will flow in the same direction. Yeah, so
I
this
see.
not happen.
Thank you.
Okay, excellent. So Burkhard, please ask your question.
Yeah, very nice talk. And in the first part, very fundamental, you showed dispersions. This was Magnum dispersion. So where does the nonlinearity come from? I mean, you are probably fully in the exchange regime for these materials. So you say you got the nonlinearity from the crossing, but crossing by itself doesn't give nonlinearity. I didn't fully understand.
Okay, so
the exchange modes.
So maybe I should go back somehow on this. So this is my backup computer, and somehow I don't see you when I show the screen. So that's unpleasant, and I also have troubles.
Simply type 5 return.
Yeah, let me go directly to the correct slide. So let me show you some Magnum Spectrum. Oops.
I mean, that is not Landau-Lifshitz, isn't it? That is far away from Landau-Lifshitz.
Oh, sure. No. The Magnum Spectrum is the same as, so whether I say I do Magnum Spectrum or I do Landau-Lifshitz Gilbert equation, that's the same thing.
Is there long wavelengths? So.
These are the excitations which are correctly described by the Landau-Lifshitz Gilbert equation.
Okay.
And and we use the inherent nonlinearities in the system, so nothing else. And we just did a straightforward calculation and actually also simulation of Landau-Lifshitz Gilbert equations. So
okay, then I understand. It's just the crossing, just the overlap in frequency, which enhances in this case is nonlinear.
Yeah, so maybe I should say that you really need. Sorry, I'm now searching for the. Here we have these spectra. Yeah? So these crossings occur in this undriven system, and in the so this is the plot in the undriven system, and what I just have in the undriven system as a condition is this resonance condition of 2 Magnum emission. Yeah, so I apply a uniform drive for this oscillating magnetic field. You have my gigahertz radiation, and that now can create pairs of magnons, and coupled by the oscillating magnetic field. Yeah? And it's important that we have a non-collinear magnetic structure. Yeah? So because then I can, in a non-collinear magnetic structure, I'm kind of guaranteed that I get coupling by my external magnetic field driving. Okay. And that is
parametric pumping, what you do here, a certain kind of parametric pumping, what you do here.
Exactly, that's not, so obviously this is nothing we invented here. It's just resonant pumping, nothing like that. Yeah? But the point I want to make is that this is now not specific to this system, but kind of any non-collinear magnet which you pump, and if you do this calculation, you get the same type of instability, and you will naturally get these type of Magnum lasers out. And the simulation confirms there's also a regime where this happens. Now, obviously, when you drive too strong, then heating and chaos and whatever sets in. But there should be always this. I think it's very generic to have this Magnum lasing regime somehow, somewhere.
Well, thank you. I just wanted to understand for your system what is happening there.
Very good. So Armando, go ahead and ask your question. And please, anybody that wants to ask a question, please raise your hand or write your question down, please.
Nice talk, thank you. I would like to, that's a technical question. How do you treat the disorder? Is it numerically or do you have some analytical?
No. So what this was, okay, so there were, so this order comes in two different ways. Yeah? One is it provides a pinning for the helices. And for this, we haven't done any numerics and no analytics in this regime. I was just stating my argument that we know that the pinning force in these materials are so small that we are on the safe side. Materials like manganese silicide. That was part one, very important, and I think certainly deserves more careful thought. Also didn't think very carefully what happens on the surface of the crystal, but whether you get some extra pinning there, that could also be dangerous. And the second part was when I now have this screw being in action, and we have now a metal, and this metal has a little bit of is dirty, and we have to ask how much charge is transported in this dirty metal. And there we used good old-fashioned diagrammatics, and which in technical level we ignored vertex corrections. So, and if you ignore vertex corrections, it just means you broaden your Green's function a little bit, and that's it. Yeah? And vertex corrections give a correction, but it will be only order 1 maximally, so it will be not a big deal. It will just change the prefactors a little bit by 50% here or whatever, which is beyond what we cared about. So,
Okay,
so it's diagrammatic. So we took it into account diagrammatically and ignoring vertex corrections for laziness reasons.
Okay. So I have a question, I guess, since I haven't seen this hanged up. So Stefano Bonetti was a talk a few weeks ago where he was measuring this mutation that if you include this in the damping term, essentially this extra d squared dndt massive term that's actually there, they were able to observe this mutating as it is processing. They have this mutation by this driving field. Is there any connection to that in this driving system?
So obviously, I don't know, but let me repeat whatever I said is very generic. So any driven system of sufficient complexity naturally develops these extra frequencies when you drive it sufficiently strong. Yeah? So I'm sure it must have shown up in many simulations and calculations before.
Yeah, it's actually not. I think in the experiments, there was a recent experiment actually. Also, it's the one that talked that is like 2 weeks before you. All is in there. So like, take a look at it. Take a look at it because I was quite curious because that generic, when you see this, besides the screwing that you have in there, you also have this mutation in there, in that motion. And this comes naturally from looking at the energy equation, not just the massless one, but the one that you include a massive term that comes naturally from the equations that has a inertia, a small inertia that comes naturally in it. And this one actually gives rise to that. I don't know if then it will be connected to that. Of course, it's not driven at all by any of your chiral systems, chirality, but I was curious of that. Okay. And the second question on that related to your suggestion of lasering magnons. Yeah. In that case, what is then the equivalent? How am I to think of this population inversion that you see in the lasing?
So lasing. Okay, so lasing is something. Okay, so population inversion helps. Yeah? So that's one way to get it, but you can just pump something resonantly that works as well. Okay. So whether the source of energy comes from a population inversion or somewhere else is not so super important. And also laser is not a fancy word. What it just means is we have a time dependent.
Right. Okay. That's what you mean. Okay.
Experiments of the Hildebrand's groups. These are also beautiful Magnum lasers, if you prefer this word. So
this is just coherent pumping them. Okay.
It's a coherent state which oscillates in time. I think that's
the that's
so like the electric field oscillates.
Okay. That I get it then.
In the same way we have here these magnons, and it's really this resonant emission here of pairs of magnons which does the job.
Excellent. So Gisela, you have a question? Yeah.
Thanks for this very nice talk. Can you hear me?
Yes.
Yeah.
I have maybe a silly question. if this is a generic thing, for example, the charge transport, if you have a good oxide, where there are no free carriers, where does the electrons come from?
Yeah, so obviously, if you have an insulate, well, we know that most of our magnets are, if you like, unfortunately, metals. But if you manage to get an insulating magnet, insulating ferromagnet with the helix, then obviously there's no charge transport. Yeah? And then we should think about rather spin transport and heat transport instead. So I was, now in this part, I was thinking about the metal. Manganese silicide was the concrete material I had in mind, where we have helices and where we drive the system, and then we have, yeah.
But you can get then in a metal charge transport very much easier via an external voltage.
Yeah, but well, I guess the better example would actually be you take a solar cell to get charge transport. Yeah? So that's what we are playing the solar cell game. Yeah? So somebody is pumping some light onto the system, and net effect is that we have heat transport. Yeah? So the solar cell is the more concrete analog for that. But you're completely right. So charge transport, I think I would go for the charge for really trying to, well, I said there are two goals in building these machines. Goal one for me, the primary goal is really to understand fundamentals of German matter, yeah, and making proof of principle experiments, seeing that I can build an Archimedean screw. And for this, charge transport is ideal. Yeah? So because you just apply a voltage probe and then you see the voltage and it's big and jumps to your yeah, so it's impossible to miss. Well, if you seriously think about applications, then indeed we should think more about spin transport. That I would completely agree with you. Then this charge transport is, I wouldn't know what application that has. Yes? That's more proof of principle thing and doing a good experiment. And then you can study these Archimedean screw. You can study how efficient they are. You can maybe look for instabilities and stuff like that. So that's a perfect system. But if you really think about applications, I think you have to think spin, not charge.
Okay, thank you.
Okay, one more further question from me, if you don't mind. So then now, we're motivated maybe for looking for things that are insulating, right? So we know that there's many more antiferromagnets that are insulating available. So since this is so generic, have you thought about the repercussions to do this in antiferromagnets?
Yeah, so they have not worked on it, but the claim would be very clearly take any incommensurate. So you want to take an incommensurate antiferromagnet, obviously, because that has the sliding motion. Yeah, and then I think you're guaranteed when you go to some, well, then obviously now you want to go to some resonance frequency to enhance the effect. And now your natural resonance frequencies are obviously now a completely different frequency range. Yeah? So we were talking gigahertz because that was this spin orbit driven wavelength system. So maybe you have to go to terahertz. But otherwise, it will just work like that. Same calculation, same everything, but different frequency range. So it has to. So if the symmetries are sufficiently low, there's also an issue. You know, the ferromagnet, the antiferromagnet.
Yeah, but I'm just curious how the exchange enhancement will play a role here.
I think
in the effect, whether it's stronger or not.
Yeah. So I think ultimately, any drive will do the job, but so the things you have to fight against is that your soft mode is an antiferromagnet. So the one thing you have to fight against is definitely the issue of different frequencies. Yeah? That's one thing, and then there's some reduction factor from the very fact that we don't excite on the staggered period. Yeah? So, but will be fine. Yeah? So my claim is it would work. So if you can start a simulation today and just try it, and you'll see it will incommensurate antiferromagnet driven by an oscillating just magnetic field. You have to think that symmetries are sufficiently low, and then it should work.
Okay, excellent. Well, I think we're at the end of our time. I think I'm going to stop now this streaming and thank all the 132 of you that were